Namaskar my dear friends. Let us talk about PIC16F microcontroller. This is very popular microcontroller from Microchip devices. Okay, so Microchip technology has come up with lot of like 8-bit microcontrollers that has been legacy microcontroller as well as very popular microcontroller for small applications and engineering academic projects as well. So the device that we will be seeing is PIC16F877A, and this is a 40 pin PDIP package. So this is the particular device that is there. Okay, and this is very popular because it has a very sturdy application and very sturdy device it is. However, the newer device is available, which is PIC16F 18877 and also PIC18F47Q10. So these two devices design is also available with us. However, what we will do in this particular session is we will try to understand the complete circuit design with this particular microcontroller so that you can have a complete understanding about how to proceed with circuit designs. Alright, so once we open the circuit, you can see this is a complete circuit design that I have already done. So this is the device, and it has been this particular symbol has been taken as it is, like pin number 1 to 20 and then 21 to 40. The thing is, as you can see, this is the particular thing which is called as reset. Okay, so let us start from beginning. What we will do is, instead of directly proceeding it to the circuit design, like what are the different aspects of these circuits and everything, what we'll do is we'll first try to understand the features of this particular microcontroller. Then we will see different peripherals, like how to design the reset circuit or UART interface, or we have push buttons, we have dip switches, we have PWM controller, or PWM output to control some peripherals, we have LEDs, then we have crystal oscillator, we have power management, like how to like give the input for power supply and then regulate it to 5 volt and 3.3 volt, all those things. Then we have several other applications, like we have a buzzer, then we have ADC, how to buffer them and put filters. Okay, and how to interface with other like daughter cards or something like that, or maybe sending it to outside board, how we can interact this one. Then we have two applications like digital temperature sensor and analog temperature sensors. Okay, so this complete circuit design we will see one by one, but before that we'll try to first understand the features and like capabilities of this particular microcontroller and why this is so like popular and why this is so useful. That we'll try to understand one by one. Okay, so let us get into the microcontroller like features and all these things. So once we open the product page, what we see is this is the product page that will be shown for this particular device, which is PIC16F877A. However, the microchip technology itself actually recommends us that we can go ahead with newer device, and that is nothing but PIC16F18877. Okay, so this is the device that will be a direct replacement for this particular one what we are going to discuss now. However, this is very useful because it is recommended for automotive design as well. Okay, if you see the complete part number, you can go ahead with this one, which is going to be PIC16F877A-I/P. So I/P is going to be minus 40 degrees centigrade to 85 degrees centigrade. Now if you have to increase the temperature, then I will be replaced with E, that will be E/P. Okay, so this is extended temperature range. So this is the two devices that we are actually going to discuss. If you have other package requirement like 44 pin package, which is like a PLCC package, TQFP package, so 44 pin package is also available, as well as 40 pin also is available. Okay, so TQFP 44 pin and PD package 40 pin is available. If we talk about some of the features, then some of the features are recommended here directly is you can have 2 PWM of 10 bits are there, then we have 256 bytes of EEPROM data memory, we have 25 milliamperes of sink and source like current capabilities. So the thing is, this particular microcontroller IOs pin having 25 milliamperes of current capabilities, that is very good one. Okay, and it has a self programming, and as well as it has parallel slave ports. Okay, so parallel slave ports will be utilized for your data communication or data interfacing. Okay, The thing is, this particular microcontroller can be used for your 3.3 volt application as well as 5 volt application. So in this particular session we will be trying to use my VDD voltage, which will be 5 volt. Okay. Other parametric like features, you can see it has 14 KB of program memory size. It has 368 bytes of RAM, 256 bytes of like data EEPROM. We have 40 pin like pin count. Maximum voltage it can take up is 5.5 volt, and minimum voltage it can take up is 2 volt. So basically it is suitable for your 3.3 and 5 volt application. Now if we talk about, it has a ADC resolution bit which is 10 bit, ADC channel, total number of channels are available which is 8 number of channels. It has it does not have actually zero cross detection, and it has 2 number of comparators as well as one SPI communication interface and one I2C communication interface. Okay, and rest all are actually not available. However, if you talk about the programming and debugging capabilities, then it can be utilized with MPLAB X IDE. So this will be utilized for your software programming. It has XC compiler as well, so programmer and compiler are available free of cost. Okay, so which is actually open source, so this is very easily available. It can be programmed using your ICD5 debugger or like PIC16F877A debugger, so that is not a problem. More of the features, if you want to go ahead, then you can directly download the data sheet and try to understand like what are the different features that is available. So you can see it has 4 devices that is available. One is 873A, then 874A, and 876A, and 877A. So we will see, we will give you the comparison. However, my recommendation is to go ahead with the highest one, which is PIC16F877A. Alright. Rest others are fine. This has operating speed from DG to 20 megahertz clock. Okay, and if you see, peripheral interface is already like already I have explained you. PWM it can go ahead up to 10 bits. Okay. All right, so now we are actually now ready to go ahead with the more into this particular circuit designs. Okay, so let's get into this. If you talk about pin configuration, it has a capability like a availability of 28 pin device as well. So as I told you, like 873 and 876A, so these two devices are available in 28 pin package. Okay, so if you need less number of pins, then you can go ahead with 28 pin package. However, generally I recommend you to go ahead with 44 pin package and 40 pin package. So 44 pin package, if you see, it has QFN package, which is pins will be inside the like package. Okay, my target device would be this one, which we are going to discuss right now, because this is very popular for your student perspective as well as like a sturdy device. It will be very strong also. Okay, so handling is very easy. Now it has port A, B, C, D, E. Okay, and this is the target device that we are going to discuss. As you can see, it has two power supply pin, which is VDD and VSS here, and one more VDD VSS here. Okay, and rest other pins are there, which will be like reset pin and then programming pin, and all other peripherals pin are there for your, like, let us say, clock input output. We have IOS pin, and we have like ADC input output pin. So all those ANA pin will be actually acting as a ADC pins. Okay, so these are the things that we have to understand before getting into the complete design. Now, as I already told you, the comparison between different devices. So as I told you, it has 873, 874, 876 and 877. Our main purpose is to work with this one. Okay, so rest others, you can see operating frequencies are almost same for everyone. We have reset in almost same. Program flash memory is highest in this particular one, which we are going to discuss, which is 8 KB. Data memory is there, which is 368 bytes of data memory in this one. We have EEPROM, which is the highest, 256 bytes. Okay, then it has interrupt capabilities of 15 interrupts are there. It has IO ports, you can see we have maximum number of IO ports in 877A. Then it has timer as well. So timer, 3 timers are there. It has capture, compare and PWM modules, that is 2 numbers of PWM modules. Then if you talk about serial communication, it has MSSP and USART, that is like serial peripherals, and UART is there. It has parallel communication also, that is your parallel slave ports communication. Then it has analog to digital modules, that is like total 8 number of channels are available. Analog comparators are there, that is 2 numbers of them. Instruction set, just 35 instruction sets will be required to write this complete program. Okay, and packages you will see, then you have 40 pin PDIP package, then 44 pin PLCC and TQFP as well as QFN. So all these packages are available. If you want to go ahead with bigger package, always look for PDIP package as well as TQFP package. Okay, anyway, this particular block diagram we have already explained you in our previous session, so this is right now I'm skipping right now. Or roughly you can see it has timer 0 1 2 3. So just now whatever I explained you these things, okay, so those all are there inside here, like how ports are assigned, like port A, port B, port C, port D and port E. Then we have parallel slave ports. We have data EEPROM. Then we have capture compare modes, we have synchronous serial ports, we have USART, you have comparator, we have voltage references. Okay, and inside this complete circuitry is there, digital circuitry where program flash memory comes up. Then we have instructions registers, then we have instruction decode control and timing generation, oscillator is there. Okay, we have reset circuits and power supply circuits. Then we have multiplexer and arithmetic logic units. All those things are there inside. We have RAM file registers, we have 8 label stack is there, we have program counter, we have data buses. Okay, so all these things are a part of block diagram of this particular ICs. Now if we talk about circuit design, so in this circuit design what we'll try to understand is, we'll try to see what are the like power management. So power management we'll see, then how to do programmings, reset, push buttons, dip switches, LEDs connections, and communication interface we'll try to understand how to connect for I2C, SPI, UART. We have parallel slave ports for data communication purpose, we have LCD interfacing, then we have timers, PWM, then we have buzzer, like for alarm purpose and all you can connect buzzers as well, then temperature sensor application and ADC applications. So all these things we'll try to see one by one. So if you talk about this particular device, so this is the target device that we have talked about, which is PIC16F877A, right? And in this particular like pin description, if you see, so pin description I'll just take out this one little bit outside. Okay, okay, so this particular pin description if you see, we have oscillator pins. Okay, so oscillator pins are there. Then we have, so anyway this we will be discussing while designing the circuit, so just I'm just going to skip this right now. Okay, coming back to other pins, we have like pin names and then package is there here, PDIP. So let me just give you only one explanation. So let us say I'm going to talk about PB0. So PB0 has the capability of PB0 pin and interrupt pin. So if you see pin number 33 is PB0 pin, and PB0 has a digital IO pin as well as interrupt, that is external interrupt capabilities. Okay, similar to that if you see, let's say PB3 pin. So PB3 pin is PGM pin, that is nothing but there are something like that, PB3 which is digital IO, and PGM that is your low voltage ICSP programming enable pin. So basically PGM will be used for ICSP programming enable, and PGC is also going to be for programming which will be used as clock, and then PGD which will be used for programming data. Okay, so PGC, PGM and PGD, these three pins will be utilized for your programming purpose for this particular IC. TTL is nothing but your like logic label which will be used for your, let's say, 5 volt logic label. If you want to use for 3.3 volt, then it will be called as CMOS logic label. So it is actually capable of both 3.3 volt as well as 5 volt capabilities. Okay, so you can see it has a CMOS input otherwise as well. Some other pins are also there, so same way you can like discuss about all these pin configuration and which pin can be used for your like USART. So USART can be utilized with C. This is your RC6 pin which can be have a capability of UART pins. We have SPI pins, so data input SPI, data output SPI, which is their RC4 and RC5. Okay, then it has I2C also, so that is I2C SDA, and SCL will be there which is I2C. So this is the thing that you have to understand which pin is having what capabilities. So once you go to table number 1.3, okay, or 1-3, all these pin names and their description is actually given. Okay, So let's get rid of this particular thing. Now what we'll do is we'll directly get into this particular design implementation. So this is the particular design that we have actually seen. Okay, so what we'll do is we'll start with one by one, and just be very careful. Now I am going to discuss how to approach to design this particular circuit. Okay, so let's get into the design. First of all comes up power management. Okay, so power management, what I have done is I have taken a power supply connector. So 2-pin connector is there, which I have named it as VCC, which will be, let's say, 9 volt to 12 volt will be input. Okay, from this input we are going to convert this using LM7805 to 5 volt. Okay, so 5 volt will be coming at the output. Okay, so this will be my 5 volt. Now this 5 volt also I have given a provision to convert it to 5 volt to 3.3 volt regulator. So one more LDO I have utilized to convert it to 3.3 volt. Okay, so there are some capacitors that have been used that we will already know, like this is aluminum like aluminum electrolytic capacitor 220 microfarad. This is ceramic capacitor 0603 package you can utilize. Okay, this is again aluminum electrolytic capacitors which will be 47 microfarad. This is 10 microfarad plus 0.1 microfarad I have used. Okay, good. So power management is done. Coming back to the MCU side, so MCU side, this is the particular symbol that I have used, and what I have done is I have taken all the peripherals or all the IO pins as well as different functionality pin name outside. So RA0 is basically nothing but like RA port or RA0 pin port. Okay, so similar to that RA1, RA2, all these things are there. Now let me give you first understanding is reset. Okay, so reset, what it happens is if you want to reset this particular microcontroller, this reset pin, which is called as MCLR pin is pulled up. Okay, and what happens is once you press this particular push button, then what will happen, this particular pin will be pulled low and this microcontroller will be like resetted. So if you do not pull it up, then it will not be starting. So make sure that this is pulled up always. Okay, there are some open drain pin which must be pulled up. So RA4 is the pin which is open drain pin in this microcontroller. So I have pulled it up so that you can utilize it as IO signal, and if you are utilizing it as output pin, then you must pull it up, then only it will go high, otherwise it will never go high. So that's the reason I have pulled it up by default. Okay, then we have programming pin. We have like MCLR pin, that is reset pin, and data pin, clock pin, and power management pin, right? So just now we had discussed PGM, PGC, and PGD. So these three pins will be utilized, which is here PGD, PGC, and PGM. Okay, so this will be used for your ICSP programming. So this is called as in circuit like programming. Okay, ICSP programming, or even ICD debugger will be able to program this particular microcontroller, so that is nothing to worry about. We have used one 12 megahertz like oscillator to generate the clock pulses for this. So clock input is OSC1 and OSC2. OSC1, OSC2 is connected here with this particular oscillator. Coming back to the power supply, so power supply pin is VDD1 VSS1 and VDD2 VSS2. So these two pins have been supplied with 0.1 microfarad capacitors. Additionally, you can attach one like extra 10 microfarad capacitor, will be good. Then this particular section is actually nothing but a pot has been used, like a potentiometer has been used, or a variable resistor has been used. So RF5 is acting as a like ADC input. So this ADC input will be actually like checking what is the voltage level at this particular node. So what I have done is this particular VDD, which is 5 volt, will be converted based on this voltage division of this this resistor, and this resistor division will be giving after this low filter. This is my low pass filter, which is 1 kilo ohm and 0.1 microfarad resistor RC filter, and then it is going to go to analog like pin, which will be checking what is the analog voltage at this particular pin. Other pins are like we have SCL pin, that is nothing but your I2C SCL, like clock line for I2C pin, and then I2C SDA line is there here. Okay, so this was all about this. Then we have UART pin as well. So UART RX and UART TX pin is there. So complete circuitry I will show it to you in the PDF. So this is the section of the circuit. Very important thing comes up is push buttons and dip switches. So push buttons I have used here, like two push buttons are there which will be going to user push button 0 and user PB1. Okay, so user PB1, what it is seeing right now is this is going to the microcontroller. So you will have like this push button. So once you push it, what will happen? This push button will be putting it ground. So this push button MCU will be seeing low whenever this is pressed. So whenever it is not pressed, it will be seeing high through this particular 100 kilo ohm resistor. Now whenever this particular push button is pushed, then it will be seeing low, and you can take some actions. Let's say you can run some LED on, or maybe take some interrupt action or something like that. So similar to that, user push button 1 is also put. So this is a great idea to like design a circuit with push buttons like this. There are some features like deep switches. So you know, like sliding this switches, it will make sure that it is switched on or switched off, something like that. So let us say this user deep switch 0, 1, 2, 3 are there, which is connected to your microcontroller, and these are all pulled low, right? So whenever it is pulled low, it will be seen that it is like 0, and the slide switch is towards 1, 2, 3, 4. Now whenever this slide switch, you will push it towards this side, like 8 side, then what will happen? This 5 volt will go and then go to this 0 dip switch 0. So the settings will be done like 0, 0, 0, 0. Then as soon as you push it this side, then what will happen? That one will become 1. So rest other will be 0. So this is how you can change the settings or change the logic level using these 4 lines. Okay, so totally you will have total 16 logic levels that you can set. Okay. Coming back to LEDs, so LEDs, there are 3 configurations that I have utilized. So first one, let us say this one. So this user LED 0 or LED 1 can be like connected directly to the microcontroller, and this will be driving the LED. So once it goes low, like microcontroller pin goes low, then what will happen? This will complete the circuit and LED starts glowing. Once it goes high, then it will not complete the circuit, like it will block it, and this is how it will not glow. Okay, so this is how it will work. Other configuration is this one. So what will happen is, whenever you can put microcontroller high, then this LED will start glowing because it is connected or source from the microcontroller IO. So microcontroller IO is acting as a source. Here microcontroller IO is acting as a sink. Okay, so microcontroller can act, IOs can act as sink also, as well as source as well. So acting as source, you can do this one. Let us say you want to learn a lot of things using like microcontroller IO. So what you can do is, instead of directly handling the LEDs through microcontroller IOs, you can send it through the MOSFET as well. So MOSFET, what will happen once you make it high, then this MOSFET will start working, and this is how this LED will start like glowing, because it will take complete path. So this, once it goes high, this MOSFET will get switched on, and this is how it will get sorted. And you can change your resistor value based on your convenience, like how much current you need to drive this particular LEDs. So this configuration is actually utilized for understanding purpose, like how to control the MOSFET. As at the same time, this is also utilized to drive high current LEDs. Let us say you need some 20 milliamperes of current or something like that. You can design accordingly resistors, and then you can send it. So you don't have to utilize 2 resistors. 1 resistor will be enough. Just for the simplicity purpose, I have taken 2 resistors here. Now coming back to the temperature sensor. So this is a temperature sensor that I have used, LM73CI MKX. Okay, so this is anyway like older device, but however this is very good one. So it has a capability of I2C, like a communication interface. Okay, so what happens is, whenever the set value, let us say you have set this particular temperature range using SDA and STL line, that is your data line, to 50 degrees centigrade. So what will happen is, as long as my temperature is less than 50 degrees centigrade, it will be high because it is pulled high, right? Now if it goes beyond 50 degree, let us say 55 degrees centigrade, then what will happen is, this alarm pin will be pulled low. So as soon as this alarm pin will be pulled low, then what will happen is, this particular alarm pin will go to my microcontroller IO, and this microcontroller will understand that okay, my temperature sensor has exceeded the temperature of the environment, and that's the reason this alarm pin has been indicated. So either you can run the buzzer using the PWM enable or something like that, or you can give some indication for temperature beyond limit, right? So this is how it is working. Understood? One more analog temperature sensor I have used, which is LM35, which is very popular device. So 5 volt directly you can give it with 10 microfarad and 0.1 microfarad capacitors. I have put it here. If you want, you can use this one as 1206 package and this one as 0603 package. And after one LPF, that is low pass filter, I am sending it to my ADC line, and this ADC line will be actually seeing what is the value of my analog value, and accordingly it will map to the values of corresponding values of temperature. Okay. So there are a lot of circuits using LM35. So the LM35 circuits have been actually given from the data sheet itself. So as you can see, it has 10 millivolt per degree centigrade. Okay, so as you can see, we have the pin numbers and pin names for LM73 actually, and just now we saw the application circuit using this SM bus I2C and SM bus interfaces, right, using this particular digital temperature sensor. So if you see, there are some equivalent circuits that is there on each pins. So we have address lines, we have ground pin, we have VDD pin, we have SMB clock or nothing but SCL line, and we have alert pin, that is your alarm, and we have SMB data, that is your data line for I2C or SM bus application. Okay, so this is how a complete understanding is there inside the datasheet that was there. Anyway, we have lot of requirement for your alarm buzzers as well. So as you can see, we can put one PWM signal here from the microcontroller, which is used as RC2 pin, and this particular PWM will be sending let us say 2.73 kilohertz signal. Okay, to 2.73 kilohertz signal will be utilized for driving this particular magnetic buzzer. So this magnetic buzzer will be using this diode as a freewheeling diode, and this resistor I have put it just for like not used purpose right now, because some of the times there are other kinds of transducer that may need resistors instead of diodes. So in that case you can remove this and put this. So designing the board becomes very easy having all the options. And this particular BC847 transistor will be actually making sure to switch on, switch off, and keep a beep sound for this. If you want, you can utilize MOSFET as well at this place. So you can utilize, let's say, 2N7002K. Okay, so this particular MOSFET, or like BSS 138 also can be utilized for this particular switching purpose. Coming back to the next one, which is ADC application. So what I have done is, the power supply was there for the microcontroller, which is VDD. So this is my 5 volt label. Okay, 5 volt label. So this 5 volt label is voltage divided using these two resistors, and after that always it is a recommendation to put some buffer and then send it to an LPF filter or low pass filter, and then send it to my analog input pin. So RA pin will be utilized as, RA0 will be utilized as analog to digital converter pin of the microcontroller. These two more ADC pins has been utilized, like ADC0 is coming from external interface and ADC3 is coming from external interface. I will show it to you. If it is already buffered, or maybe doesn't need any buffering or something like that, after low pass filter I have sent it directly. One more provision is, you can do after buffering, you can send it to the RA1 pin. Okay, and selection of this particular op-amps and all depends on how much bandwidth you need and what is the working voltage you need. So those things will be discussed later. Right now you can directly go ahead with this design. There is one thing that I already told you, like I have one external interface so that it can be connected to external devices or maybe switching on something. So I have sent a signal from my microcontroller pin to enable that device, and I am getting output or feedback, so that whether it is on or off, that will be indicated to my microcontroller line. Okay, and there were two ADC lines that were coming from that board, so that will be utilized here. At the same time, you can see I have sent the same power supply from my board, like our microcontroller board, to that device, so that that device can be powered up through this particular power itself. Okay, so all these things one by one you saw. Now let me just open the circuit where you can see very easily a complete design that is there. Okay, so as I told you, this is the reset switch. So if you want, you can put the part numbers as well, so that you can have a complete understanding of how it is. And I have put a resistor in series also, so this can be utilized to make sure that it doesn't immediately switch off or some, I mean reset or something like that. It takes little time to switch off. Similar to that, we have UART interface. So UART interface, these two pin can be utilized to have UART communication, and they have been already pulled up with 4.7 kilo ohm resistors. This is the programming connector that we have utilized. And coming back to this is the pin which is utilized as open drain pin. So RF4 is used as open drain pin. I have added one extra 10 microfarad capacitor here for a better purpose. Then we have potentiometer to utilize as analog to digital converter testing. Here I have made little changes, like I have made some safety as well. So putting fuse in the line is always a good idea. So I have used one fuse in this line so that it can save this particular circuits if there is over current or something like that. And this particular jack input, I have put it one diode here so that both of them are connected together, then it can be avoided, any short circuit can be avoided. So what will happen is, let us say voltage at this point is more, then this particular voltage will be used. If voltage at this point is more, then this will be used. Okay, so this is how it will be working. Anyway, one of them is always recommended to put, not both of them, so you avoid putting both the power supply together. Many of the places you will see that VDD has been used as 5 volt, but however for better purpose sometimes what I do is I use net name as 5V. So what I have done is I have used one resistor, so this VDD can be supplied through this resistor and net name change will happen, which is 5 volt. So 5 volt will be utilized everywhere. And these are the push buttons, then dip switches, and PWM controller PWM output is also there. So this can be sent to some PWM drivers or something like that, where you can send your PWMs. Similar to that, we have SPI configuration, UART configuration lines. So pin numbers are there, which is particularly assigned for those purposes. We have I2C line. So actually I2C line only is used as SPI as well as I2C both. So either one of them can be used for one purpose. So what you can do is, I have connected it to I2C SDA. Now you remove this particular resistor and connect this RC4 to your SPI line so that it can be used for SPI purpose. Okay, so same way I have used this side also as clock as well. So either you can use SPI clock or SCL clock, so any one of them can be used. So to use SCK clock like SPI clock, what we will do, you will remove this R106 and connect it to RC3. Understood? And slave select for SPI, it is this pin. So if you want, you can utilize this SPI SS pin to go for slave selects. Alright, so in the second page, this is the alarm thing, and then we have ADC section. So this is the ADC and external connection section. Coming back to next part, it is my digital a temperature sensor, and this is my analog temperature sensor. So hope you have a particular idea and particular understanding about this particular microcontroller and how to design this particular circuits. So if you do have any questions or anything regarding the connections of this particular circuits and how to interface the design and how to select a particular pin for a different purpose, okay, so those things you can put down your queries in the comment box and we shall be giving you the answers. However, before closing to this session, what we will do is, we will give you a brief comparison between the devices that will be actually discussed later. So we have just now discussed PIC16F877A, and this is a 40 pin device PDIP package. However, this is not recommended now because it is going to be obsolete. So you can utilize always PIC16F177 or otherwise PIC18F47Q10. So this is much more advanced one compared to this as well. But this will be direct replacement for PIC16F877. So you can see we have taken from Mauser Electronics. Okay, so Mauser Electronics has given the particular comparison between these three devices. So you can see we have part numbers, then we have manufacturer, then we have description, which is 8-bit microcontroller, all of them. Then we have data sheet. If you want, you can directly take it from there. Life cycle, you can see it is not mentioned here, however it is going to be obsolete, so that's the reason I am giving you this comparison. Then we have ADC resolution, that is all of them are 10 bits. Then we have same manufacturer, we have core is PIC16. Then we have DAC resolution, so DAC is also available in this one. Okay, so that's the reason I am telling you this is best one. So this is 5 volt 5 bit DAC is there. We have data bus width, which is 8 bit. We have data RAM size which is now increased to 4 KB and 3.53 KB, okay, compared to this 368 bytes, and both of them are having data RAM types which is SRAM types. Some more comparison is there which you can see here, like PIC16F877 and this one. So we have data ROM size which is all of them are 256 bytes. Then we have data ROM type which is EEPROM type. We have interface types. So interface types, all of them are having this earlier one what I discussed is I2C, SPI and UART. However, this one is having all those. In addition to that, we have RS232 and RS485 as well. Okay, so this we will discuss as soon as possible. We have clock frequency also. Now it was up to 20 megahertz, it has changed to up to 32 megahertz. Then maximum and minimum operating temperatures are almost same for both of them. We have mounting style of all of them are through hole because they are pin to pin compatible. The best thing is ADC channels. So almost all the pins now is capable of getting assigned as analog channels. So 35 channels are there for ADC pins. It had only 8 channels. Okay. Now number of IOs are total 36 IOs are there. Out of 40 pins, 36 can be used as IOs. Rest 4 pins are those like power pins that cannot be used as IOs. Okay, and here only 33 were there. So package you already saw. Then product is microcontroller. We have product type 8-bit microcontroller. We have program memory size which is more now. So it was just 14 KB and now it is 56 KB. And all of them are flash type memories, and then we have qualification. So this is AEC-Q100 qualified, means it can be used in your automotive as well. Okay, so automotive application it can be used. The best part is it has two series. One is LF series and one is without LF series. So L means 3.3 volt and without L means 5 volt series. Okay, rest others you can see minimum voltage and maximum voltage operating range is same almost for both of them. So this can be used only for 5 volt application, but this can be used only for both of them like 3.3 volt as well as 5 volt application. Okay, so this were all about this particular like 3 comparisons that I wanted to show it to you. So alright guys, just get into this particular session and enjoy your complete circuit design for microcontroller. So whatever the things that were required to start with the microcontroller design, and each and every sections, and whatever the possibilities that were required, let's say push button, dip switches, LEDs, or temperature sensor interfacing, or like buzzer implementations, all these things I have tried implementing this. We will see more applications like LCDs, timers and all those applications in our next sessions. Thank you so much.